Hello, I am Dan Hulea, and in this video I will continue the presentation on hybrid DC-DC converters with an example of storage applications using one of the already presented hybrid converters. In this presentation I will start with a short introduction on storage applications and their role in microgrid structures. I will then continue with an overview of the most common microgrid control strategies. Then I will focus on the main control strategies developed for this purpose, which are decentralized and based on Drupe control. These are the conventional and nonlinear Drupe control and the conventional and nonlinear virtual impedance control. For these strategies, I will then show the control implementation and the experimental results which we obtained, and I will end the presentation with the main conclusions. Many applications for bidirectional converters are for storage purposes in renewable energy applications, which are usually integrated in microgrid structures. A means of managing the power flow within the grid by controlling the converter is required in order to manage the source of production or storage, to reduce energy costs, to increase efficiency, or to increase reliability. Hybrid converters are especially useful for supercapacitor storage applications. Therefore, the focus of this presentation will be on supercapacitor storage strategies. Microgrid structures are commonly categorized from the communication interface perspective, more precisely by where the energy management decisions are taken. Within these categorizations, microgrids can be centralized, distributed, and decentralized. The centralized microgrid, as the name suggests, has a central control system which communicates with all converters and distributed generators from within the microgrid and measures all electrical parameters from the system. Information from each unit is acquired in a single centralized place. It is processed and commands are sent back to each local controller. This system requires a well-developed communication interface to the faster but localized controllers to which relevant information regarding the power transfer is sent. Even if it requires a central control unit, which is also a single point of failure, this is still by far the most common used control strategy. The distributed strategy has a better resilience compared to the centralized structure, as here the decisions are distributed between all the local controllers, which also communicate within a network. The higher decision level controller and the lower faster current voltage controller share the same unit. Lastly, the decentralized control strategy uses local controllers which do not communicate between them within a conventional network, but rather they communicate by changing parameters of the grid, for example in these systems by changing the voltage level. Even if they can operate individually without a central controller, they are still commonly integrated in centralized systems in order to create a more efficient system and to reduce the communication speed from central to local controllers. This presentation focuses on decentralized strategies as they are most suited for small-scale, small power applications, and the Drupe power sharing methods used for these strategies can be upgraded in centralized or distributed structures. The Drupe control was developed as a power sharing strategy by emulating the Drupe characteristic of synchronous generators and was later used for DC converters where parallel operation of multiple modules was required. The method was also used in various papers as a decentralized control method for microgrids. The standard Drupe in DC voltage controls the converter so that it has a voltage variation proportional to its output current around the prescribed voltage VD. This is similar to an ideal voltage source which has a series resistor connected at the output. This control feature is done by lowering the output voltage reference with respect to the output current. As we see in this characteristic, as the current increases, the output voltage decreases because of the emulated resistor which is in series to the ideal voltage source. Again, it is important to remember that the resistive characteristic is implemented in the control strategy, and it is not an actual resistor connected in series to the converter, as that would greatly increase the losses. This next section presents two different power sharing strategies for supercapacitor storage, with a simple or more complex implementation that are decentralized and based on the standard group control method. The requirements that inspired the creation of this method were to create a control method that will limit the charge and discharge of the supercapacitor in the usual voltage operation range and increase its charging currents when approaching the bus voltage limits. To achieve this requirement, the Drupe methods with the characteristics from this figure were developed. Here we can see that the converter operates like a conventional linear Drupe between the two voltage limits, but when the voltage would increase some more, the maximum charging current set in the converter will be available to charge or discharge the storage element. The ideal schematic of this converter of the nonlinear Drupe method uses a larger Drupe resistor, Ra, and two Zener diodes connected in series to each other and in parallel to the resistor. With this schematic, the method operates similarly to the conventional Drupe, but when the voltage limits dictated by the Zener diodes are approached, a larger current will limit further variation on the bus by charging or discharging the supercapacitor. An important aspect to mention is that the ideal voltage source, VDA, is a current limited voltage source when implemented in the converter. With this implementation, the charging mainly occurs when the bus voltage are above certain values. Because the nonlinearity of the Zener diodes might be too harsh, the nonlinear method can be implemented using a nonlinear resistor, RB. This virtual resistor can be mathematically designed with different functions to behave, for example, as a varistor and to have the static characteristic presented in this graph. As shown above certain limits, the converter operates in constant current mode, but within it is behaving as dictated by the mathematical function. For this purpose, the power function or the arctangent functions can be implemented. Because trigonometric functions are widely used, some microcontrollers have a hardware implementation of them. For example, the C2000 family of Texas Instruments. The control implementation for the nonlinear strategy with Zener diodes is shown here in the diagram. The control loop uses a cascaded current voltage control with the saturation block set1, which is used to limit the IL1 maximum reference current from the inner current loop. The actual Drupe implementation contains the RA gain and the SAT2 saturation block, which are multiplied by the IL2 current, which can be approximated to the current from the voltage bus, high voltage bus. The resistance gain represents the actual resistor from the equivalent schematic, and SAT2 is used to simulate the breakdown voltages of the two Zener diodes. The voltage Drupe is added to the voltage bus and then subtracted from the reference, which in this case is connected to the high voltage output of the converter. The nonlinear resistor method is implemented in a similar way to the Zener method. The cascaded current voltage control is also used while changing the calculation for the voltage drop. Here the inverse tangent function is used, as this will result in faster calculations from the controller that was chosen for this application. And here the IL2 current is also used as an approximation of the current from the high voltage bus. The first hybrid switched capacitor converter is used for testing the Drupe methods, as it has inductors on each output, and the currents are already available for measurements because they are state variables and are considered for control purposes from the initial design. The parameters for testing the two methods are enumerated in the table for both nonlinear Drupe methods. These parameters are used in the static gain characteristics and in the control loop implementations. Here we can see that we have a voltage on the high voltage bus of 350 volts with a maximum voltage variation of 20 volts. The Drupe resistor has a value of 3 ohms and the current has a limit of 3.3 amps. And we also have the characteristics for the nonlinear resistor parameters, which is designed to be similar to the Zener diode method. The test setup used for this method is shown in this diagram, and it consists of a supercapacitor bank with the CSC capacitance, the bidirectional hybrid switch capacitor converter, BHSC1 for short, a bus capacitance, C-bus, a real Drupe resistance, R-Drupe, and a parallel combination between an electronic load and a DC source connected through a diode. The purpose of the Drupe resistor and the parallel combination of the source and electronic load is to emulate a conventional Drupe controlled grid, and the real resistor is used for the grid side in order to reduce the complexity of the test setup, while the nonlinear resistors are programmed in the microcontroller, of course. The specifications of the equipment used in the test setup are presented in the next table, and here we can see that the supercapacitor has a capacity of 63 farad with a maximum voltage of 125 volts. We have an electronic load with a maximum power of 2.44 kilowatt and a DC source with a maximum power of 10 kilowatt. Both the load and the source have a maximum voltage of 400 volts. The C-bus capacitor has a capacity of 10 millifarads, and the Drupe resistor has a maximum resistance of 4.4 ohms. For simulating the operation of the two strategies and for implementing the digital control on the microcontroller, the PSIM software was used. This greatly simplifies the design and helps to achieve a better resemblance between the experiments and the simulation results. The simulation is too complex to be shown, but it contains two main parts. The actual power converter electronic schematic which contains all the main components connected to an emulated DC grid, and the digital control, which is then implemented in the microcontroller. The control has then few other components, such as the voltage and current controllers, the actual nonlinear Drupe control, the additional current and voltage limits, and the configuration blocks for the microcontroller peripherals. The simulations on the left and the experimental results on the right show the operation for the linear range with the Zener strategy for currents smaller than the current limits, and we see here that a smooth operation is achieved. On the graph we see the voltage on the voltage bus, the current on the output of the converter, the supercapacitor voltage, and the current on the supercapacitor. We also see a very good resemblance between the simulation results and the experimental results. When operating in constant voltage mode at a larger current, at plus minus 5 amps, we see that some dampened oscillations are shown for the currents of the converter, which is expected because in this range the virtual resistors is considered to be zero. But in this case, the bus voltage is still limited to 340 or 360 volts. The oscillations are the main reasons for which the next method was developed, even though it was expected because of the harsh characteristic of the Zener diode. Here we see the results for the nonlinear resistor method. On the left side, we see the results for lower currents for plus minus 2 amps. And on the right side, we see the results for higher currents for plus minus 4 amps. The results on the left, as we can see, they are very similar to the Zener method, but we see a difference on the right side where the oscillations are no more present. With this method, the same voltages are achieved during the two regions, with the difference that for the second method, the current and voltage oscillations are greatly reduced. And of course, a smoother transition is achieved. Therefore, we can conclude that the nonlinear resistance method does not introduce the same oscillations during the transition between the charge or discharge modes. The static characteristics of the two methods are presented in these figures for the Zener method on the left and for the nonlinear resistor on the right. A good correspondence is shown between the theoretical and the experimental operation, with the exception of the constant current operation for the Zener method. The difference for the constant current operation comes from the fact that the IL2 current is not actually limited, but actually the IL1 current is limited. These limitations are calculated based on the fixed limits for IL1 current and the maximum power limitation. With this condition, the maximum current values are variable within a small range when the voltages at the two inputs are drastically changed, as the duty ratio is also changed, and so is the ratio between the two currents. The limits are to be considered as a safety feature for protecting the converter, and the IL1 current is chosen because it is the larger of the two currents. Newer methods for introducing supercapacitor storage in Drupe-controlled microgrids propose the use of virtual impedances in place of conventional Drupe resistors, achieving a virtual impedance Drupe-controlled method as a power-sharing controller. Here we see the equivalent schematic of the virtual impedance Drupe control method placed in a conventional Drupe control grid. The commonly used impedance for this method is a series resistor capacitor circuit, which achieves a high-pass filter for the currents flowing to the converter. With this filter, only high-frequency variations from the DC bus will be used to charge or to discharge the supercapacitor, while the low-frequency currents will flow to the rest of the grid. Based on the virtual impedance Drupe control and the nonlinear resistor Drupe presented earlier, we proposed a nonlinear virtual impedance Drupe control method with this equivalent schematic. This method works similarly to the virtual impedance Drupe control, with the difference that the nonlinear resistor helps to achieve a variable cutoff frequency that depends on the amplitude of the voltage. The variable cutoff frequency will make the charge or discharge process to operate at currents depending on the voltage variation and implicitly the power fluctuation in the grid. If lower power variations are present at a specific moment and implicitly there are lower voltage variations, the supercapacitor influence can be designed to be lower with this method. Another option is to maintain normal operation at lower power variations, but increase the effect on higher power variations. Similar to the nonlinear resistor drupe, a nonlinear virtual impedance drupe can be used with a different type of nonlinear resistors. The control loop implementation is similar to the implementation for the nonlinear drupe with the Zener diodes or nonlinear resistors, in the sense that it has a cascade voltage current control and the virtual impedance is used in the place of the nonlinear resistor. Here the voltage on the virtual filter resistor RF and the virtual capacitor CF are added because they are connected in series. The resistor voltage drop is calculated simply by multiplying the current and the resistor value, and the capacitor voltage drop is calculated by integrating the output current. The implementation of the nonlinear virtual impedance drupe control method is similar to the conventional virtual impedance drupe control implementation, with the difference that the linear filter resistance is replaced by the nonlinear function, defined in a similar fashion to the nonlinear drupe method, as an arctangent function. The experiments are performed in a similar way, using the same converter and the same experimental setup, but a different control strategy, with the parameters described in this table. Here we have the voltage on the DC bus of 350 volts and the virtual impedance composed of a virtual resistor of 3 ohms and a virtual capacitor of 1 farad. The parameters of the nonlinear function are also presented here. It is important here to not confuse these virtual components with the real capacitor, which has 63 farad capacity and is used for storage. Larger times are required in order to test the operation of the two methods. Therefore, only the experimental results are presented using an acquisition time of 10 seconds. For this time interval, simulation files would result too big to be easily handled. The design was performed such that the nonlinear virtual impedance drupe methods has a similar influence in the grid at small voltage variations and similar operation at larger voltage. The conventional virtual impedance drupe on the left and the nonlinear virtual impedance drupe on the right are compared for voltage variations of plus minus 10 volts applied to the grid, and we can observe that the currents for the latter are much smaller for this case. The waveforms presented in the graph are the same as previously. The voltage on the high voltage bus, the current on the high voltage bus, the voltage on the supercapacitor, and the current through the supercapacitor. If the voltage perturbations are increased to plus minus 30 volts, we observe that the charging and discharging currents are almost identical for both the conventional virtual impedance drupe and the nonlinear virtual impedance drupe. A special case presented here is at t equal 0 seconds, where a large voltage pulse is applied to test the reliability of both solutions. The nonlinear virtual impedance drupe gives an advantage when the operation of the converter is not required for low powers, but a higher influence is required by the converter at higher powers. The method also has an advantage for centralized systems where it gives the possibility to adjust multiple coefficients by the higher order system for an optimized operation specific to some applications. Now we will watch the test setup in operation. Here we see the bidirectional hybrid switched capacitor converter with all the sensors attached. On the scope we see all the waveforms presented earlier. We see here the inductor current transitioning from one side to the other. And we see that it has a smooth operation. Here we see the code generated from PSIM software that is used to control the converter. On the signal generator we have the time interval for the voltage variations. Here we have a real resistor in series to the parallel connection between an electronic load and a voltage source, which are used to emulate a droop controlled DC microgrid. And on the bottom we have the supercapacitor used for storage. Turning off the voltage variations turns off the converter as well. This chapter presents an overview on the energy management strategies available for microgrid applications, with an emphasis on the decentralized droop control methods. Energy management strategies are considered for the charge and discharge control of supercapacitors used in DC microgrid applications, implemented on a hybrid converter. For this purpose, two simple nonlinear characteristics for a droop control are analyzed. The nonlinear droop methods are considered as a simple alternative to the conventional centralized methods for supercapacitor storage. The virtual impedance method was improved by using a nonlinear characteristic for the filter, achieving this way the advantage of a variable influence on the storage system based on the amplitude of grid voltage variation. In other words, a variable cutoff filter frequency can be achieved with the benefit of having more control parameters useful in a centralized energy management system, or different influences depending on the voltage variation on the grid. In the end, I would like to thank you for your time and wish you all the best. Have a nice day.